Hi there. So I'm going to go through question one and question three. So firstly, we're given the non-vanishing Christoffel symbols in Schwarzschild spacetime. And using these, we derive geodesic equations. So Schwarzschild spacetime describes the geometry of spacetime around a spherically symmetric non-rotating mass, like a black hole. The non-vanishing Christoffel symbols are derived from the metric, and they hold information on how coordinates change due to curved spacetime. A geodesic is the straightest possible path between neighbouring points. So we begin with the geodesic equation, which I've highlighted in yellow here, and it is used to calculate these paths based on the geometry of the spacetime. Hence why we have the Christoffel symbols, as they adjust our predictions of our trajectories, which are influenced by the curved spacetime. So for a Schwarzschild spacetime, we get the following geodesics. By plugging in our time coordinate for mu, we get our temporal geodesic. For r, we get our radial geodesic. And then we have two angular geodesics, the polar and the azimuthal geodesics. Now, the relevance of these geodesic equations is that they describe specific aspects of motion in Schwarzschild spacetime. The temporal geodesic, for example, describes time dilation needed for GPS, and the radial geodesic describes gravitational attraction, escape velocities, and redshift. These equations bridge GR with the observable effects in astronomy, like gravitational lensing, but also it confirms the observations of those who came before Einstein, like Johannes Kepler, which brings me on to question three. So we are given a circular orbit in Schwarzschild spacetime, which lies on the plane theta equals pi over 2. Starting with the radial geodesic equation we derived, we can lose all terms which are a derivative of r because we have a circular orbit, therefore r is constant. Also, r theta is a constant because there is no variation to our plane. This also means that sine squared theta is equal to 1. Now, with a bit of algebra, we can rearrange and get an expression for our angular velocity in the Schwarzschild spacetime. Noting that angular velocity relates to to an orbital period with this expression here, we can plug in our expression for our angular velocity, which we derived, and then rearrange for t. You'll notice we now have Kepler's third law of motion. And this says that the orbital period squared is proportional to the cube of the orbit's radius. And therefore, we have verified Kepler's third law of planetary motion. Thank you.